There we go. So length and perimeter. Some of the key ideas you got to look for is like these lines that basically represent, if there's two dashes here, two dashes there, they represent the same length. And then adding them up. So if this is 90 degrees, these corners, we can actually, there is, some people may not see it as enough information for us to answer there, but there actually is. There's a fair bit of information there for us to be able to really take away with that. So what you can do with this one, and I'll show you how this basically works, is there is enough information for us to calculate this here. So what you'll see is that this is 10 centimeters because this double line represents this double line there. So far I know what this length is, this whole length here, and I know what this whole length is. So perimeter is just adding it all up. So far we've got two lots of 10, or you can do 10 plus 10. I don't really mind which way you want to do it. And if you look at this line and this line, well, this line would really go here, right? Like if you moved it across. So that total length is the same as this length. So that is 10. Similarly, I could move this line down to here. And this length is going to be the same as that length with 13, or I could have moved this line up to there. So they've got 13. So really, you know, you could add up two lots of these 10, which might be a bit tricky. I probably wouldn't go about that way. What I actually see this is this length is 10. This length and this length here is 10. So these lengths both add up to 10. And then looking at these ones, these two add up to 13. That's the same. So sometimes if you don't think you've got enough information, you can kind of slide these backwards, left or right, to make some of the lines fit into each other. So we've actually got two lots of 10, which is this one and this one and this one, and we've got two lots of 13 plus two lots of 13. So it's going to be 20 plus 26. It's going to be 46 centimeters. Now notice if we're calculating perimeter and length, it's going to always be centimeters to the power of 1. We don't write centimeters to the power of 1, but I'm pulling that out because when you're doing area, it's always going to be centimeters squared. When you're doing volume, it's going to be centimeters cubed. Why? Because length, just centimeters, means like it's a length, right? You're measuring a length. When you're talking about centimeters squared, we're talking about like how many 1 by 1 centimeters squares fit in this shape. When we're talking about centimeters cubed, we're actually talking more about a 3D space. So we're talking about how many centimeters cubed fit in here. This one would have 4. So, you know, those like each one of these is 1 centimeter cubed. Here, we're about 1 centimeter squared. And why we call it centimeter squared is because it literally makes a square centimeter, squared centimeters, I should say, not centimeters squared. And we call these cubic centimeters, and we call these squared centimeters. So a lot of people call these like centimeters squared because they read it like the maths. It's 1 centimeter squared, but you should really call it 1 squared centimeter. I got 4 squared centimeters, 4 square centimeters. There's 4 square centimeters. I got 4 cubic centimeters, 4 cubic centimeters. Because if I say 4 centimeters squared, are you talking about like a 4 by 4 centimeters squared? If I say 4 centimeters, square it, are you talking about that? You know what I mean? So that's why we use the words 4 square centimeters, because it actually makes it a lot more. Oh, you got 4 square centimeters. So we actually know we got 4 square centimeters there. I don't say 4 squared centimeters, I say 4 square centimeters. So please be knowful of that. So there's enough information there for us to help with those ones. On this subchapter, I encourage you guys to go to 5A, looking at converting between units of length. There's 1,000 meters in a kilometer, so we can change that. Obviously, kilometers, meters to kilometers, you can divide kilometers to meters. It's going to get bigger. It's 100 centimeters in a meter. There's 10 millimeters in a centimeter. So you can convert between these. And perimeter is the distance around the outside of a shape. So let's have a look at quickly some of these starters, and we'll go through some of these and get through a bit of conversion. So if you want to convert from centimeters to millimeters, there's 10 millimeters in 1 centimeter. So I'm literally going to go 5 times 10, and that will equal 50 millimeters. Meters to centimeters, that's 100 centimeters in a meter, and it's going to get bigger. So I always think, is it going to get bigger or smaller? And that really helps me. So 2.8 times 100. Move the decimal place twice, 1, 2. That's the beauty with conversion. They're all powers of 10. So you've only got to move the decimal places is really all we're doing. 1, 2, so that's going to be 280 centimeters. Millimeters to centimeters, well, it's going to get smaller. And I know between there is 10. So if it's going to get smaller, I have to divide by 10. 2.1. The decimal place is here. I'm just going to put that in just because I need to move. For every 0 I've got, that's how often I need to move the decimal place. So I've only got to move it 1, and it's going to get smaller. So that's 52.1 millimeters. Centimeters to meters, I know it's going to get smaller, so I've got to divide that. 8.3, it's got the decimal place already in there. Divide that by 100. So now I just need to move that 1, 2, because we've got 2 zeros in here. It's 2 lots of 10, really. 10 times 10 is 100. So it's going to be 0.837 meters, which is right, because 83 centimeters, as you guys know, isn't a full meter, right? It's close to, so that looks pretty good. So always use your common sense when you're converting. Think, does that seem right? So if you had 4.6 kilometers, we've actually got to times that by 1,000 to go to meters. So move your decimal place 3 spots. That's going to be 4,600 meters. 2,170 meters to kilometers. You're going to divide that by 1,000. That is going to be 2.17 kilometers. Technically, you should put in the 0 there because it is measured to that length accuracy. So I'm going to do kilometers. A steel beam is 8.25 meters long and 2.55 millimeters wide. State the length and width of the beam in centimeters. Well, it's going to be, you're going to have to times the meters by 100. So it's going to be 825 centimeters by, and we need to divide this by 10, 2.25 centimeters. So converting, just use that chart. Always use your common sense when if it's going to get bigger or smaller. Obviously, from millimeters to centimeters, I'm expecting the number to become smaller. From meters to centimeters, I'm expecting the number to become bigger. So that looks good. Given the values of the pronumerals, all angles of these vertices are 90 degrees. So what that means is, because it's at 90 degrees, all these ones in the middle, that is good. That means that basically the lengths aren't on an angle. So therefore, I know that this is going directly straight up and in parallel with this. And this one is too. So I know that this total length is going to be 6. I know that this total length is going to be 10. If you look at it, we've got one total length of 6 and another total length of 6 with those two. So we've got 2 lots of 6. And we've got one total length of 10 here, and this one, that makes 10, and another one of 10 here. So you've got 2 lots of 10 plus 2 lots of 10. So it's not asking for it to calculate the perimeter, but I'm just trying to show it. Give the values of the pronumerals in these shapes. So really we want to find out what A is down here. Now, if you know that that is 10 and that is 7, this has to be 3. So A equals, well, we know the total length, because if you look at the length of A, let's just go back a bit. I should just erase this out. Oh, don't want to do that. So if you, no, I didn't want to do that either. So if you just look at the length of 10, so really what you've got is you've got this length of 10 here, and then we've got a length of A, and you've got a length of 7. So we know that A is going to be, well, this total part. If you take away that, you're going to be left with just this part. So if I start off with 10, and then I take away the 7, that's going to equal A. Alternatively, I could also write an equation saying, well, 10 equals A plus 7. And I could use some algebra to solve this. 10 minus 7 equals A. Because we know that this length is the same as A plus 7. Solve it, A equals 3. So many ways to go about that one. Here we know that B is equal to 3 plus 3. So you can set up an equation and just solve it. And that's kind of where we start using algebra a bit. Just trying to introduce some of the basic things, and you'll find later on it will get a bit a bit more challenging, but it's really just coming back to your basic laws of area and perimeter. That's why we're going to be doing this week, and then trying to get to D at the start of next week, and then we'll be going back into algebra. Here we're trying to find out length of A. Well, I know A is equal to what? Well, I know that this is the same length as this, so A has to equal 12. B though, B has to equal, B plus 8 has to equal A. Now we already know that A equals 12, so I can substitute that in. So therefore, B would equal 4 minus 8 from both sides, which is the same thing as going, well, 4 plus what would equal 12, right? Over here, I presume this B is referring to this length, maybe, or that length. This is a bit confusing. This is where you need to clarify.
There's 2 lines, which means it's the 3.1 meters.
Yeah, I know, but I don't know if B is referring to this side or if it's referring to this side.
It has to be on the right.
I think
right?
I think it's the one on the right.
I reckon it's got to be the one
B
on the
has
right
to
too.
be, yeah.
I think you guys are right, because otherwise it's just B's 3.1.
Yeah.
You know, anyway, it's an
It
ambiguous
has the 2
question.
dashes as well.
Yeah, but it still could be. Yeah, I know what you're saying. So A has to be obviously 6.2, right? Sorry, the total length has to be 6.2 of this 3.1 and 3.1. 6.2 for A. So B, if it's the one on the right, would be what? 5.9 would need to equal to B plus 3.9. Hopefully you guys can see that, because this total length has to equal, we're saying that's B plus 3.9. So B would equal 2. Nice. So hopefully you can see how this works. You guys seem to be getting the hang of this anyway, which is pretty good. Let's quickly move on to the next subchapter for you guys. Again, those keynotes are really important. So this is out of the next subchapter. This is those keynotes where I would encourage you guys to go to. When we're looking at the circumference of a circle, I normally, hopefully in year 8, you guys would recall that if you look at the diameter, if you take that diameter, right, and then you say, hey, how many diameters fit around a circle? You'll actually find that there are 1, you'll have 1, 2, oh, that's a bit bad, 3, about 0.14 will approximately fit around there. So if you look at the diameter and you go, hey, if you look at any circle, doesn't matter how big it is, that's a bad circle. And you take the diameter, right, you'll still find that 1, 2, 3.14 pretty much will fit around there. So they came up with this number called pi. And pi is basically how many more times the diameter will go around the circle of the circumference. So if you take that and you multiply by how many times the diameter will fit around the circle, that is what pi equals. Pi is how many times the diameter will go right around the circle. Hence, the circumference equals diameter times pi, because this number tells you how many times the diameter goes around it, which is 3.14. Like if you pull up your calculator, that's how pi was invented. It was invented purely for that reason. Some people still don't know that, and I think it's amazing that you don't. But that 3.14, literally, if you drew a perfect circle and you took the diameter and put a string around it, you would find that it would fall around there 3.141592654, and it keeps on going on and on times around a circle. That's what pi is. I mean, pi was designed for that. It's kind of funny that they called it pi too, like P-I, not P-I-E, because, you know, I could understand if someone goes, oh, if we cut it, oh, but, you know, you've got, anyway, you get what I'm talking about. So the, you know, pi is a relationship between the diameter, and that's how many times it goes around. It's actually, you know, 1 times the diameter here, another diameter goes here, another one here, and 0.14 roughly diameters go there. So when I try and think of a total circle, if I've got a circle with a diameter of, like, say, I don't know, 4, well, I know it's going to be approximately 12, because 4 threes is 12. So really, you know, that's what pi was designed for. So, I mean, if you take the radius then, you know, well, there's 2 radiuses make a diameter. So 2 radius is the same thing as a diameter. So 2 radiuses times pi will give you the circumference as well. And that's where that comes from, the formulas. So pi was literally invented to answer this question is, if I have a circle of whatever width, how far would it be to go around the outside? Well, there was no perfect number, so we created this symbol called pi to represent it. Originally, back in the day, it actually used to be 22/7, and that lasted for a long time. And then they disproved that that number wasn't accurate because it was pretty close for many, many years. You know, you look at that number there. What have we got? 22/7 is 3.14. Let me just do it on the other calculator, then we can look at both of them together. It was really, really close, this relationship. And they're like, oh, that's a perfect fraction to use. So a lot of history for hundreds and hundreds of years, they were using 22/7. Like we're talking about, this is, you know, a good 1,000 years of maths we're looking at here. And we're learning it in like 5 minutes, which is, I think, absolutely fantastic. You know, and that's what we do a lot in maths. We compress so much learning. So you look at the difference here. They sort of thought, oh, this is the perfect number for the pi. So it's 3.142857. You know, these numbers keep on going on. Well, that one recurs. And this one here was 3.14159. So it's, you know, it's pretty damn close. You know, especially now we've got algorithms. I think they've got it to something like 3 billion digits long, and it never occurs. Like we're talking about 3 billion numbers after this. So they still haven't perfected pi, like as a number. So, you know, it's an irrational number because it just never ends, and that's why we just give it the symbol. That's why typically, you know, if we say, hey, there's, you know, what's the width? If you want to give an exact answer of exactly how far around the circle this is, well, if the radius was 2, right, you'd call that 4 pi. That's my exact answer, because I can't give this any more exact than pi because it just doesn't end. So, you know, I could say it's 4 pi centimeters. That would be an exact answer. So hence this 22/7 or 3.14 can be used to approximate pi, right? Or use technology for more precise calculations. So it gives you a good approximation, because at the end of the day, I mean, if you're building a fence around like a circle, you know, you're going to have to end it to some nth degree, and near enough is close enough as long as you join them up, you know. So if you had to build fencing and say it was like, you know, 13.2788885 meters, you just get 13.3 meters, right? And you'd probably just tie it up and have a bit of slack in there. So difference between application, you know, in doing it in the real world, and having something a bit different. So a sector is a bit different, which is what we're going to look at. A sector is just a portion of it. You have a minor sector, which basically, if you talk about a full circle, the minor sector is like the smaller part of a circle. So that would be your minor, you know, sector, and this would be your major, because it's a major part of it, and that's a minor part of it. So you've got 2 different parts as well. How do we calculate it? Well, if you think about like actually what we're trying to do, if you look at this part of the circle, well, we can actually calculate that part. I mean, if you want to calculate the total perimeter of this, you just go, well, the total perimeter of this, well, because it's in terms of radiuses, it's going to be 2 pi. Sorry, it's going to be 2 times your radius times pi, because it's your diameter by pi, right? Because remember, your diameter, pi fits around them. However, we've only got a small section. Well, what section of that do we have? Well, we've got, just say if that was 60 degrees. If that was 60 degrees, well, you'd use 60 degrees out of 360. Or if it was 90 degrees, it's a quarter of a circle, right? If it was 90 degrees, you'd use 90 out of 360. Now, if you simplify 90 out of 360, that's actually a quarter. And that's why it makes sense. So really all we want to do is we actually put a fraction in front of it. How many degrees of the perimeter of a circle you want to do out of 360, because this is the fraction of how much of a circle you have. And that's your formula to find out this part. Then don't forget, if we want to find out the perimeter, we also need to add the 2 radiuses. So we have a formula. We've got the 2 radiuses, which refer to these parts. And then you've got to add on the fraction of the total perimeter, the fraction of the degrees you have of the total perimeter. And that's just going to give you this part, just that part there. So this whole bit gives you just that part. So that's how we calculate that one. The symbol of pi can be written and easily extracted. Yeah. So yeah, if you had a radius of 2, 3, sorry, we've got a radius of 3. That means the diameter will be 6, so it would be 6 pi. So that's how we get exact answers. So that is in your keynotes. I think it's pretty important. We'll just go through a couple of examples here. So really, you know, if you're looking at this, how much of a fraction of a circle do you have? Well, 90 degrees is taken, so you're left with 270. So you've got 270 degrees. So to find out the length of this, you would have 2 lengths of 4, 2 times 4, plus you'd have 270 on 360, which is 3/4. Same thing, but you can put this in your calculator, times by 2 times the radius, times by pi. You put that in your calculator and you'll get your answer. So I'll do one of these in the calculator, and that's the only one I'm going to do. So 2 times 4. Now plus, think of BIDMAS. I want to do that first. That gives you 2 times 4. Bring up your fraction button, 270, hit down to go to 360, on 360, hit across, times 2, times 4, times shift pi. Notice I've hit the shift because it's yellow, pi. Alpha will give me any of the blue things. Yellow will give me any of these yellow ones. Some people have different calculators, but there is a shift to get there, and you'll find pi around. It gives me an approximate answer there, okay? So that's approximately, and then I will write, notice the symbol that we use is not equals. We do like a squiggly line like this, okay? It's an approximately equal to, because it's not exactly equal to, 26.85. Now, is there any units on this? No, there's not. So I just leave it like that. I don't write centimeters and meters because there's nothing there. So this one here, if we're looking for the perimeter, we've got 2 lots of 6, which gives me this. Plus, I've now got a fraction of 60 degrees of a circle on 360, times by 2, times by the radius, times by pi. Because that's giving me the whole circle, but I'm only taking 60 degrees of the whole circle. Here, we've actually got 180 degrees. So we've got 2 lots of 5 again, which is just 10 centimeters for the diameter. That's the whole length. Plus, we've got 180, or a half, I could say, because 180 over 360 is a half, times 2 times 5 times pi. So that would be 10 plus 5 pi. That would be it as an exact answer. If you had to simplify it as an exact answer, it'd be 10 plus 2 for 5 pi. You can't write any more than that. In your calculator, you can get an approximate answer. This one here, we don't know what this is, but we can use algebra still to figure this out. So we know that the length of this is, well, it's 2 times the radius. That will give me these, 1 lot and 2 lot. Plus, I've got this much of 360 degrees of a full circle. So what's the answer for a full circle? We've got that of a full circle. So the answer for, of a full circle, where was I? Here. So that is times the diameter. That's the diameter. 2 lots of radius times by pi. So that gives me the full perimeter of a circle, but I only want that many degrees of it. And this is actually a formula, if you realized. So that's it. Have a crack at some of those ones. I left you guys some questions. Hopefully, if you got any questions, do you have any questions? Anyone got any clarifying questions?